סיפורים זה אחת. Welcome everybody. Okay. We're gonna get more technical today. Some of you are going to love it, some of you are going to get quite confused. So we'll do all we can to make it not confusing, or as little confusing as possible. Okay, we're going to go down today to talk about photons. First thing first. So what we're doing now is talk about Maxwell's equations, photons, Planck-Gordon, and Prop equations. QED in short. Quantum electrodynamics. Now, what did we do last time? So we spoke about units. Right? We said we prefer to work in Heaviside Lorentz units. Then we took the Heaviside Lorentz would be our main units here. Then we spoke about covariant form of Maxwell's equations. So the Maxwell equations you know look like that. Nabla dot E is equal to rho. That's Gauss's law, right? Nabla cross E plus ETB is equal to 0. That's Faraday. Gauss, then no magnetic monopoles, and then Ampere. These are the Maxwell's equations you know and love. But we wanted to give them a slightly different form in order to make them fully Lorentz covariant, which means that they are easy to transform from one frame to the other. And what we do for that, we introduced a new what's called a tensor. It's called the Faraday tensor. With two upper indices. F mu nu, where we just ordered all of them in a simple way, right? 0, E1, E2, E3, minus E1, minus E2, minus E3, and then zeros on the diagonal, minus B3, B2, minus B1, and opposite. B3 minus B2 plus B1. Of course, 1, 2, 3 stands for X, Y, and Z. Then we introduced two new 4 vectors. One is called the current 4 vector, J mu, which is rho and J. And that enabled us to write down the two homogeneous unhomogeneous Maxwell's equation. So that plus that we wrote down in a simple form d mu f mu nu equal J mu nu. For those of you who are less familiar with that, it's mainly with the notation, right? With the summation here, I remind you, over mu. For those of you who are less familiar with that, go and do it at home. Actually do it. See that these exactly give you these two equations. The great advantage of that enable an immediate transformation from one frame to the other. You know automatically, if I give you the electric and magnetic fields, you know how to transform them from one frame to another frame. So if you're ever wondering, given an electric and magnetic field, and now an observer is moving, or an observer is seeing a source of electric and magnetic field moving towards him, what would be the electric field and magnetic field. That's what it's going to see. Another thing which you can automatically see from here is that if there is one frame in which there is only an electric field, another frame, a magnetic field will appear. Okay? They are connected. So this can be a specific case when there is only an electric field, but when things are moving, a magnetic field will appear. Okay, so that's why they are together. Then I introduce something which you're supposed to know, I guess, which is the idea that of potentials. Since we can write down B equal nabla cross A, and E plus ETA. Yeah, okay, minus fine. We introduce another 4 vector potential, A nu, which is phi, and A vector. So these are the potentials. We do not measure them, we do measure the fields, but we can use them. And when we write the potential, we can use the other 2 homogeneous Maxwell's equations as f mu nu is d mu a nu minus d nu a nu. You may be wondering, what do we gain by doing all that? What's wrong with this old Maxwell's equation after you spend a lot of time memorizing them for the exam and learning how to use them? Again, this is extremely useful, not only in relativity, but also in quantum fields. Of course, because this is what we can quantize. And this is the fact that these equations are completely consistent with special relativity, and this Lorentz transformation is automatically seen from here. Right? This is not seen directly when you're looking at that. Right? I'm sure that you've heard that one of the advantages of Einstein's special relativity was that the theory is fully consistent with electromagnetism. Right? Okay.
So
now, yes.
If you say that we can only measure the fields and not the potentials, but how does it go well with the Aharonov-Bohm experiment?
Yeah, Aharonov-Bohm experiment is quantum mechanics. This is classical.
Ah, okay.
In quantum mechanics, then the potential gets quite important. And Aharonov-Bohm was a great demonstration for it.
What did you say?
What?
What did you say? Can you repeat what you said?
Yeah, I said everything we're doing here is classical. But this is classical. This is the same as Maxwell's equation. Aharonov-Bohm is a quantum mechanical effect. Okay? And this does demonstrate the fact that the potentials have physical meaning, indeed. Okay? Classically, we only measure the fields. Right? Potentials, we treat them as calculation tools. Right? Then we said we can write down this Maxwell's equation as d mu a nu minus d mu a mu is equal to j nu. That's basically the inhomogeneous Maxwell's equation from here. Just plugging it here in here. Now we said, since these potentials are not measured directly, right? We have a freedom. This is called a gauge freedom. The guy who invented it was Hermann, or found it was Hermann Weyl. And we're going to encounter his name in the coming weeks. And he showed that we can make a transformation. That's called a gauge transformation. Gauge is a scale. It's changing the scaling, basically. A mu, go to A prime mu, which is A mu, plus d mu lambda. So by adding a function lambda, this will not change the physical results. So we have some freedom.
The physical result is the J.
The physical result will be the electric and magnetic fields and the J, of course, the current. Okay? The measurable. physical result, I mean what we can measure. Okay. Now, well, we can use this gauge symmetry to make some selections of what values of lambda we'll have, and it's an arbitrary choice, and this will help us make the equation look better. So one is called one such choice of lambda is the one that will give us. You can choose lambda such that d mu a mu is equal to 0. This is called the Lorentz condition.
You cannot always choose that, right?
I can.
But if I will give
Classically,
you
I can.
a case that a current that
Classically, I can.
okay.
And then we have, with this choice, we'll have that the Lambertian of A mu is equal to J mu. And if there is no currents, then in a vacuum, J mu is equal to 0. Then we have the Lambertian of A mu is equal to 0, and this is a wave equation. So the for potential A mu obeys the wave equation in vacuum. Everything we did so far is classic. Okay? Then towards the end I said, okay, questions about it. So this is, if you don't get that, then the rest you won't be able to get anything. It's
Just
mainly mathematical manipulations. The importance is that it's really it's built into the formalism of relativity. Yes.
Just edge case if the electric field goes like 1 over r.
Yeah.
So phi is lambda. So it not converge at an infinity, right? So can you still do the trick?
Yeah, you can always do that.
Okay.
It's a mathematical manipulation.
Even if
this
the
is-
potential
If what you give is not
exploding?
physical, I will get a non-physical result at the end.
Okay.
But the mathematically, there's nothing that prevents me from doing that.
Okay. Fair enough.
Okay. This is, I just set up.
It
This
happens
is
when you
this is
have
a definition.
cylinder with a current. So
This is a definition. Yeah, you can do that.
Okay.
You will not get a physical result, possibly, but you can do that. Nothing prevents you from doing that. Right? You just define it, and you take the Maxwell's equations. These are Maxwell's equations. They're just written in a different form. You just manipulated them in a way that makes them look more compact and more easy to transform from one frame to the other. If I get an equation that is correct in one frame, I know how to transform it to another frame. That's all. It's the same equation. Yeah.
The final wave equation you got there is basically 4 independent equations for each component, right?
Yes. Essentially, yes. But is it 4 equations? Yeah.
So the electric potential is independent, is basically can be independent of, or each component can be independent. I mean, I could present a solution with all 3 zeros and 1.
In a given frame.
Okay.
In a certain frame, yes. Like you can think of, again, I don't know if you've seen that. This is something which you should have seen, but you may have not seen. Right? Let's say I only have a point charge. Right? It's not moving. Right? Then I'm going to get only an electric field. Right? According to Gauss law. I put here a point charge, plasma ball, then I measure an electric field, I'll get here some electric field. If I measure a magnetic field, what I'm going to see? Zero. Now I'm transforming. Now, this is me, right? I'm sitting here. Now I'm transforming to a different frame. Now I'm moving. What's going to happen? I'll get both an electric field and a magnetic field. Right? Now, did you see the transformation of electric fields and magnetic fields? This is something which you're supposed to see in, we call it classical fields. Right. The transformation is given here, according to these equations, because you know how it transforms. So making a transformation here is automatic. It's a simple mathematical. I should give it to you in the homework. Just do it. See it. It's easy. Yeah.
Why does it mean that you can always have only electric field nor magnetic field?
No, I didn't say always. I said in a given frame, there can be a situation. There can be a situation.
But they're not always.
Of course.
You don't always have a frame.
No. There can be a situation where in a given frame there is only an electric field. Okay? But this is not a general. If I go to another frame, in that other frame there will also be a magnetic field.
Local.
No, not okay. Everywhere. You're measuring. Okay. We are measuring in one place in space.
Okay.
Right. The simplest way to think of it, completely classical, right? In a frame that I'm moving, I will see this point charge moving towards me, right? Point charge moving is a current. There is a current. The current produces a magnetic field everywhere in space. Okay. This is classical. Now we want to quantize that. Now there's going to be certain tricky and nice points around here. So first I said, okay, Schrodinger's equation, right? We started by taking Schrodinger's equation, deriving Schrodinger's equation. Schrodinger's equation, basically we took the energy and momentum, promoted them into operators that operate on a wave function. And there was a question, so I just write down Schrodinger's equation, right? Minus h bar squared over 2m, lambda squared plus v, psi is equal to I h bar d t psi. So I was asked, why do I do it for energy and momentum? Somebody asked me here.
What are you using? Why are we?
It's Schrodinger's equation. You've seen
No,
it.
why we don't use the natural units?
Not to confuse you more than anything. Yes, I'll put in 1 here. Okay? I don't need, because it's not relevant anyway. It's not relativistic. But I just want to give you the idea, right? So I took the energy, I took the momentum, turned them into operators, right? E turned into minus I h bar dt. B turned into minus I h bar lambda. They work on wave function. Somebody asked me where it comes from, why E and P. So first, it's not just E and P. You can also turn R to make it an operator. It actually comes from de Broglie, right? De Broglie interpretation of a particle wave, right? So wave function, we have E I k x minus omega t, right? And omega is associated with the particle's energy, and the k is associated with the particle's momentum. So that's the origin of where it comes from.
It's k vector and x.
K vector and x vector. That's where it will come from. At a deeper level, conservation of energy implies symmetries in time, and conservation of momentum implies symmetry in space. I'm not sure how much we'll have time to.
And energy is with plus I, not minus I.
De Broglie, omega is E is equal to h by omega. I want minus here. Minus.
Okay.
Does that bother you? Anyway, you take the size. When do you take the size website to
Yeah, exactly.
Yeah.
You take size.
Doesn't matter.
So you don't care. For you, it should matter, because if you make this mistake in an exam, then you're screwed. For me, I don't care. As long as you understand what happens here. Now, what's the gauge, right? Now, if we try to do the same for photon, since this is massless, right? We had E squared minus P squared is equal to 0, which we wrote in a covariant form, P mu is equal to 0. You realize that what's written here is the same.
Just the null.
This and this are the same, just a different convention. Just a way of writing, right? Because P0 is E, Pi is P. Because there is a down case here, there is a minus sign. Yeah? Make sure that you're fully familiar with this notation. Then we end up that this gives us minus d mu, which is minus D'Alembert-Yan. So the equivalent of Schrödinger's equation for photons is D'Alembert-Yan of A mu is equal to 0. This is where we quantize. Right, we turn P, this is classical relation. This is still classical relation, just written in a different way. Now we took P, turn it into an operator. This is no longer a classical equation. This is a quantum mechanical equation, the same as Schrödinger's equation. This is an operator, D'Alembert-Yan, which operates on A mu. So the same as the operator here operates on the wave function psi, the operator D'Alembert-Yan operates on A mu. So now we have a new interpretation. A mu is now interpreted as what?
Wave function.
As wave function of the photon. So A mu, so as opposed to the classical wave equation. So now we A mu, just to write video with all these pens. A mu is interpreted as a photon wave function. That's how we look at it. Questions? This is how much we got last time. I'm spending time because I think these are definitely things that you did not see. Pretty sure about. So it's worth spending more time on. And they are not that trivial, not that easy. Questions? No? Sure.
Is there more of a reason to interpret a mu in such a way other than just the D'Alembert-Yan is a 0?
No, 0 is vacuum.
No, I'm
0
asking,
means that there are no sources.
Is there a deeper reason to interpret a mu as a wave function of a photon in a vacuum other than just the fact that the D'Alembert-Yan is a
This is no.
0? No, you understand the mathematics, is this the only reason we want to interpret a mu this way?
I'm not sure. I mean, one thing I can tell you, right, if you look at it in terms of Feynman diagrams, for example, right, if the full equation is here, right, if there is no vacuum, then the Lambertian of A mu is equal to J. It's a general. Right. Which basically the interpretation here is that the photon is associated with currents. Right? So currents can either generate photon or a photon can decay into a current. Right? Which, you know, you can visualize in terms of Feynman diagram. Right? So this can be something like that, right? This is the things we've seen. This is a generation of photon by a current. Right? You have an electron and positron. Or you can have an electron photon that decays into an electron and positron. We can have a scattering. These are Feynman diagrams essentially will be interpreted as connection how to generate or modify properties of photon by interaction with currents, electric currents.
None of these are legal.
Why? All are legal.
I mean, an electron and a positron turning into a single photon, is that allowed?
If it's a virtual photon, then yes.
Oh, virtual, okay.
You think I'm going to do illegal things here? Yeah, just technical. So A mu represents a photon, right? And A mu is a what type of quantity? Or vector. It's a vector. Right? So we said that the photon is a vectorial particle. So the term would be that the photon is a vectorial particle. A mu is a 4 vector, which means that the photon is a vectorial particle, or we simply call it a vector. Again, that means that when we Lorentz transform from one reference frame to another, then we know automatically how the photon will be transformed. The photon in the sense of how the representation of the photon will be transformed. And that leads us to another term, which is that the photon is a 4-dimensional representation of a Lorentz transformation. 4-dimensional it's an S, C-onal representation of a Lorentz transformation. That's another technical term. Okay, now note that we could have written something like nabla of phi is equal to 0. Phi is a scalar function. So it's not the same. Right. This photon is a 4 vector. If it's a 4 vector, let's find a solution to this 4 vector. Right, solution to essentially this equation. The solution is going to be presented by a vector. What's going to be the interpretation of the different components?
Potential.
Probability. No, you're not. It will be the polarization vectors. Photons have polarization. Yeah. So we're actually going to derive the polarization out of the photon. So let's see how it works. So in this framework, again, this is part of QFT, I agree.
It's still classic thinking.
There's no classical anymore.
Where we
I turned that into a operator.
Okay,
And I look at the four vector now. This is a mu now represent. This is
quantum physics is no longer with probability, where the probability is coming from.
Now I assume that I have a photon. Now a mu represents now a photon. Now I have a photon.
Yes.
This photon has to obey this equation, which is now interpreted as in terms of
Is
an
it
operator.
deterministic? That's what I'm asking.
You're asking a different question. You're asking what is the probability of having a photon. And I'm telling you, I'm not dealing with that question. I'm now saying I have a photon. Now I want to see how I describe this photon. A photon is given to me. What is the description of a photon in this framework? So the photon now is a 4 vector, a mu, which obeys this equation. And now this equation is interpreted in a quantum mechanical sense. Right? This is an operator that operates on a 4 vector, turns it into another 4 vector. I assume you all know what is an operator, by the way. It could be quite a strong assumption. Right? An operator takes one function and turns it into another function.
It's also linear in this case.
Yes, it is linear. Right? But an operator takes one function and turns it into another function. What is a function?
It's one object.
It takes one number, can be more than one number, and turns it into another number. Sinus x is a function. I give it an x and I get y, which is equal to sinus x. Okay? This is a function. An operator, I give it a function and I get up another function. A derivative is an operator. I give f and x and I get another function, which is df dx. Okay? Just to make sure that we're all speaking in the same language. So, now, so the solution, what do we call it? Plane wave solution. Plane wave solution. Right? So in vacuum, J mu is equal to 0. In the vacuum, we have J mu equal to 0. So the equation we have is the Lambertian of A mu is equal to 0. So we can write down the solution in the form A mu is equal to some constant A times epsilon mu of P times a plane wave, E minus I P mu x mu. Instead of using mu, then let's use something else to confuse. P mu x nu. So A, this is the normalization factor that takes all the dimensions. This is where all the dimension is. P mu, what is P mu? Momentum. Yeah, photon for momentum. And epsilon mu of P, this is the photon polarization vector. And as we're going to see in shortly, this is actually associated with the photon speed. I'm going to take you to a little bit more abstract. So let's take this solution and plug it into this equation. Show you that I'm not cheating. So this equation is d alpha a mu.
So,
Yeah.
somebody wants to join me.
Somebody want to join? Okay. Okay.
Maybe.
If you see again, then let me know. Are they coming?
Yeah, one on top.
Okay. Okay. זה מה אתה עושה?
אתה יכול להביא לנו שאנחנו נעשה את משהו?
לא, אתם לא רואים מה קורה. אתם לא צריכים להתעסק איתו. אתם תתרכזו בשיעור. Okay. So d alpha a mu. What do we get? What do we get? That one? What? Okay. לא שרגע להתפסח פה. How do I take the derivative with respect to alpha, to x alpha? The alpha is d over the x alpha. What do I get? What do I get when I take the derivative here?
G P alpha.
What?
I P alpha.
Yeah.
8p.
Thank you.
Yeah.
It's minus
5p.
minus I
P
p mu delta alpha nu. Right. D alpha, I have another alpha, right? A epsilon mu p e minus I p nu x nu.
From where the delta came from?
I took the derivative with respect to alpha, x alpha, and I have here p nu.
When you write delta alpha, you mean just
Delta alpha nu. If alpha is equal to nu, I have a 1. If it's not, then I have 0.
Should it be
We're in
an
phase space.
מה מסובך?
shouldn't it be an eta instead of a delta? Because it's a covector F.
Oh, yeah.
It's a vector. It's a, okay. You can put a
I
delta alpha
understand.
nu if you want.
Yeah.
But it doesn't. If you want to be precise, it's like that. But it doesn't matter.
oh, you switch
No, now you
the
have something.
No, yeah. Then I have a p. No, I have a p nu here. No, so it was right. It was right. You confused me. So I have minus I p alpha minus I p alpha a epsilon mu e minus I p nu x nu equal to 0. Which we get p alpha is equal to 0. So this is a solution, right? This is a solution to this equation. P alpha equal to 0 is a photon. Just said that. Right? Now, we have the Lorentz condition. Lorentz condition d mu a mu is equal to 0. So d mu a mu is essentially p mu epsilon mu is equal to 0. Right. What does it mean?
They're perpendicular.
That means that the polarization is perpendicular to the momentum. Did you learn about photon polarization just to make sure that we are
Yeah, in waves.
waves?
A bit in waves.
Who learned?
And
Raise your hands.
Taught it to
Everybody. Okay. So you know that this is perpendicular to the direction of motion.
Yeah, yes, yes.
It just proves.
Yeah.
Just written on the board. And that also means that how many independent components of the polarization vector there are? Three, right. In fact, there are two. Right. So there is still one more degree of freedom which needs to get rid of. And that is from the Lorentz gauge, right? We still have one extra degree of freedom, right? So this is the Lorentz gauge, Lorentz condition, right? But since this Lorentz condition, there is a choice of gauge, right? We can still choose a gauge. Does it mean choosing a gauge? Right? Remember that A prime mu was equal to A mu plus D mu lambda. So we can choose a gauge which is consistent with the Lorentz condition, or the Lorentz gauge, right? We can select if we have, so we can still choose a gauge lambda such that d mu lambda, which is the Bernoulli of lambda, is equal to 0, and that is fully consistent. Right? We have a freedom of selecting different values of lambda. Right?
We can choose it to be independent in time.
As long as it satisfies this condition, then it is automatically satisfying the Lorentz condition. Right? There is more than one lambda that does it.
Yeah.
So I can select, so the lambda that I select, we choose, we consider, we
yeah, it depends on t, but
choose one. So I choose,
right,
lambda of x is equal to I b e minus I b nu x nu. And b is some constant. B is a constant. P nu is a photon for momentum, which satisfies, of course, P nu is equal to 0. That's, of course, going to give us the Lambertian of lambda is just minus P squared lambda, which is 0 because P squared is equal to 0. So, for this choice of lambda, we have that A mu, we're making the gauge now, right? A prime mu, which is A mu plus B mu lambda, which is equal to what we had written. So we have epsilon mu E minus I P mu x nu plus I B D mu E minus I P mu x nu, which is epsilon mu E minus I P mu x nu plus I B minus I P mu E minus I P nu x nu, which is epsilon mu plus B P mu E minus I P mu x nu.
Epsilon is a function of t, right?
Yes.
Okay.
So that means, remember, making a choice of a gauge does not change any of the physical results. Right? So that means that the electromagnetic field would not be changed if we transform the polarization vector such that epsilon would go to epsilon plus BP. Since gauge transformation does not affect the results, the measurable quantities. They will not be affected if the polarization vector will change as epsilon mu goes to epsilon prime mu, which is epsilon mu plus b p mu. So we have this freedom of choice of polarization vector. Yes.
Can you set it to be 0?
I can.
Okay, so
What?
Can you choose the
No, I mean
a
no,
to be 0 or something like that?
No, I can select. Look, as long as I'm consistent with this condition, right? I have to fulfill the Lorentz gauge.
It's consistent. You can choose epsilon mu to be minus b p mu. So
Yeah, I'm
it
going to do
will
it
be
in a
0
second.
and
I'm going to do it in a second. Hold on.
okay. It's very
No,
simple.
hold on. Wait, it's a bit more complicated.
Is it
That means that if I
consistent
take the
with
polarization vector and I add to it some constant times the for momentum, this is not going to affect the physical results.
Right.
That's not what you're saying, sir.
Yeah, what I'm saying, if you
That's not the same.
yeah, it will. I don't see why it will.
Just follow the math for a second. Okay, what this says is that
that's
if I'm taking the polarization vector, I'm adding to it some constant times the photon for momentum, then it is not going to change any of the physical results.
Let's say that it's still perpendicular.
What? Yeah, they're still going to be perpendicular. That's what it means. Essentially, yes. So we can have several such choices, which will still conserve that, right? As you say, right? Since they're perpendicular, adding a constant constant in that direction doesn't change it. So we can have multiple such choices, but not necessarily 0, as you said. One of them is called Coulomb gauge or transverse gauge. Coulomb gauge or transverse gauge,
Why can't you choose 0?
because then it will not fulfill these conditions.
This condition will be okay. The condition.
The second condition with lambda will not be okay. Will not be fulfilled.
It will be inside the
No, it will not be.
transformation.
It will not. No, it will not be fulfilled. Okay, check it out at home, and if you still don't get it, then come to it. Now, so one such condition. So one such choice is called. We choose one possible choice is called Coulomb gauge. Coulomb gauge. And another name for that is called the transverse gauge. So we select B such as the time-like component of the polarization is 0. B is equal minus epsilon 0 over P0. These are the time-like components of the polarization vector and of the momentum. Of course, this gets epsilon 0 is equal to 0. That means that A0 is equal to 0, but this is just the time component. And using that in the Lorentz condition, right? Remember we had d mu, a mu is equal to p mu, epsilon mu is equal to 0. That is the Lorentz condition.
You have freedom on lambda, you don't have freedom on epsilon, right?
Well, that's why I just made the choice.
Yeah.
I just selected.
Yeah. Why?
What I said, right? I do have a freedom of lambda. As long as I keep the lambda with that E right here, B times E minus I P X.
Yeah, I just asked if you have only freedom on lambda and not on epsilon.
No, epsilon is what I assume this is in my photon
Yeah.
wave vector.
Okay.
This is
Okay.
this is my photon polarization vector, essentially. Right. Now I have the Lorentz condition. When A0 is equal to 0, epsilon 0 is equal to 0, A0 is equal to 0. What do I get from here? P dot epsilon equal to 0. That means that blah blah dot A is equal to 0. This is the familiar Coulomb gauge that you might have seen.
Yeah.
Yeah? So it's the same. It's just generalization of into 4 dimensions. Yeah?
Because the momentum is essentially the gradient operator. I'm not sure.
Not sure. I'm not sure that I get it. Again, what did you say?
Is it because the momentum is essentially the free momentum is essentially the gradient operator?
No.
Or no?
No. But what does that tell us? P dot epsilon equal to 0.
They're perpendicular.
So the polarization vector, right? The polarization of the photon is transverse to the direction of motion.
What is transverse?
Perpendicular.
Okay.
If this is the motion of the photon, propagation direction, then the polarization would be
Yeah. Okay. Yeah.
this direction. Yeah,
What happens if you have a circular?
it's fine. As long as it's perpendicular. Wait.
Okay.
Uh,
No, that's not.
so how many degrees of freedom do we have?
Two.
Two. Two, right? X, Y, and Z. We have 2. So there are 2 degrees of freedom. Degrees of freedom, mainly there are 2 independent quantities to fully describe the physics. Fully describe the photon in this case. Yeah? Which are 2 possibilities for polarization. Right. So, for a photon that travels in the plus z direction, right? We can get a solution as a linear superposition.
In the X and Y.
Exactly right. So all solutions, basically, all solutions can be written in terms of a linear superposition of the 2 polarized states of the 2 polarization states. Epsilon 1 mu would be what? 0, 1, 0, 0, right? And epsilon 2?
0, 0, 0.
Which is quite cool. Right? Time x, y, z. We said time is 0. For this choice of Coulomb gauge, one polarization vector in the x direction, one polarization vector in the y direction. The photon itself moves in the z direction. Of course, this is not a unique choice of basis, right? We can choose a circular polarization, which will be
Maybe in the time. No.
circular polarization of C, right? Right. Circularly polarized states. Alternatively, circularly polarized states, right? We call them epsilon mu minus is equal to normalization would be 1 over square root of 2, 0, 1, I, 0. Epsilon mu plus would be 1 over square root of 2. What will I put here? Oh, sorry, there is a minus I here and there is a minus here. It's mainly a convention. 0, 1, I, 0.
Why one is inside the vector, one is outside?
By what?
One is inside the. Okay.
I'm not sure they get it.
No.
0, 1, I, 0. There is a minus here, so it's a minus
Okay,
1,
okay.
minus I. Here it's 0, 1,
Yeah,
minus
yeah,
I,
yeah.
0. It's really a convention. That doesn't really matter. You see why. So actually, these states correspond to the z component of the spin of the photon. Write it down. These correspond to the z component of the photon spin. SZ. Now, did you learn about particles spin in quantum mechanics?
Yes. Even
Who
off vector.
did not often? Who did tell you that about quantum mechanics about the spin? Who did not see that in the quantum mechanics course? Everybody did see that.
Yeah.
You did not? Why not?
I didn't do quantum mechanics yet.
You did not take the quantum mechanics.
Ofek showed it.
Don't know what Ufek showed you. Don't rely on what he did. But it should be seen in this gives you SZ plus minus 1. Okay. Questions?
Ask a question.
What?
Can I ask something?
Yes, you can ask.
You wrote alternatively circular polarization, כאילו כתבת פולריזציה סיבובית, זה הכוונה?
Yeah, כן. Circularly polarized.
איך הוקטורים משיגים סיבוב?
You'll see that in a second.
Okay.
Yes.
The correspondence to the component of the spin is because of the magnetic field. So that would
לא.
לא.
תכף אני אראה לכם את זה. Yes.
I'm struggling to understand why there are only 2 degrees of freedom. Like, where do we see that in the equations?
Where do we see that in the equations? Well, there was, let's give me a shot. One is written still here. It's a selection of the gauge. Right? One was the selection of the gauge, and the second one just came out from the Lorentz condition itself. Right? We had the Lorentz condition, d mu a mu equal to 0.
So every equation reduces the degree of freedom?
Essentially, well,
And we start with...
no, one equation, which was, we started with a 4 vector for a photon, but then it had to fulfill the Lorentz, the Lorentz condition, right? D mu a mu equal to 0, and that would put away 1 degree of freedom. And then we had the second degree of freedom from the choice of gauge. Since we have the gauge freedom, we can choose whatever gauge we want. Okay? So really this reduces another degree of freedom. So instead of 4, we ended up with a 2. And these two correspond exactly to the polarization of the photons, and this is what we know, that photons can be polarized. Okay? More questions?
But it's freedom given momentum. It's given...
Photon is moving in some direction. It cannot be at rest. Every photon, it has some direction. Right? Photon being a massless particle cannot be at rest. Okay. Which now there were questions that I was asked, so now is the time to actually do that, and I think some of you are going to be a little bit happy for that, because we're going to get into a little bit of group theory. See the smile, right? Don't worry if you didn't learn it. I'll use some terms and I will explain that. So you'll see what they are. So I mentioned that this corresponds to the photon spin. Let me explain it. This is not a trivial statement. This you should see, right? So we have the polarization we got, right? So we have 2 degrees of polarization, 2 degrees of freedom, basically corresponding to polarized photons. We have a photon, 2 photons. One is polarized in that direction, one is polarized in that direction. Both are moving in that direction. Okay, and we can have linear. Any photon would be a linear combination of these 2 states. Okay. Fine. Now I mentioned the photon spin. I did not say what is a photon spin. That requires a little bit more physical insight and some mathematical knowledge. I tell you it's going to be a cool lecture, but more technical. Okay. So, the general solution, photon spin. So, the general solution for photon propagating in the z direction right? So, P is perpendicular to z. But V A mu is said A, B1 epsilon 1 mu plus B2 epsilon 2 mu. Epsilon 1 and epsilon 2 are written right here before I erase them. E minus I P mu x mu plus complex conjugate. Right, complex conjugate because photon is a real entity. Right? If I'm telling something that you don't know, then stop me. I assume you all know that. This is a general solution.
So A should be a real vector, right?
Yeah, ensure that the photon essentially is a real vector. You have a real photon.
Okay.
So instead of that I can simply write it as A mu is equal to real of A B1 epsilon 1 mu plus B2 epsilon 2 E I P mu x. I even omitted the minus here because it doesn't matter which one. I take it just the real
2
part.
times the real.
Nope. It's the real part. I normalize it.
Okay.
You can just absorb it into A.
I can absorb it to it.
Yeah.
Thank you. Appreciate that.
Exactly.
Okay. So we have 2 solutions, right? So 2 options, right? So one option, we can select either B1 equal to 0, B2 equal to 0. Select B1 equal to 0 or B2 equal to 0. What does it mean? Linear polarization in either the x or y direction, right? Linear polarization in either.
You can always
Make a mistake here. Okay.
choose something like that because you can
Either
just
X or y direction. Now we have another choice, which basically was written here. which I write it down as v1 epsilon 1 mu plus v2 epsilon 2 mu is equal to, I call this epsilon up, which is 1 minus I, or what I call epsilon down, which is 1 plus I. But the minus here is a convention, really. Again, of course, these are only the x and y components. I just omit the time and z components because they are zero anyway. Right?
They are not perpendicular, right?
There is a 0 here and a 0 here.
Right? Yeah. I'm asking if the
Epsilon up 1 minus I or epsilon down 1 plus I. You've seen the second one.
Yeah. They are not perpendicular.
Epsilon up and epsilon down are not perpendicular.
Perpendicular to each other, I think. Why?
הם כן, כי אתה עושה תחולה פנימית, אתה תעשה צמוד הרמיטי לאחד.
אוקיי.
מתמטיקה זה.
זה גם אותו.
מה הבעיה? Look, we reached the level that you do need to think a little bit. It won't be automatic, right? You have to look at what I'm doing, read it again at home, think a little bit, and then you realize that I'm right. Okay? You won't be able to do it. Sometimes you will, right? There are smart people in this classroom, but sometimes you simply have to take your time and read it slowly. Okay? Good. So we do have a 90 degrees phase difference between them, so they are perpendicular. So that means that the dependence of x mu would be something like a up vector would correspond to real of e I p nu x nu and real of minus I e I p nu x nu, which is what? What is real of e I p nu x nu? Cosine. Cosine p nu x nu and sine p nu x. Now, of course, there is a phase constant, etc., which I just omitted. Right, everything will get in here. Just see this. And the same for a down. Going to be proportional to. We have a real of e I p nu x nu, and then real of I plus I e I p nu x nu, which is what? Cosine p nu x nu and minus sine p nu x nu. So this will be the two vectors representing the photons. Okay, in this selection. Okay, so if I was to select the linear polarization, it will be easy. Right now I'm selecting a combination, right, which would look like that. So this is the combination, then the A mu, the part that represents the photon propagation, right, the photon 4 vector will look like that. Right? This is the x and y component, the 0, the time and the z components. Now, let's see. So let's say, remember what I'm trying to do here. I'm trying to prove to you that this is related to the spin of a photon. Now, let's assume that we have assume that the vector has a state A up at x. A up at x. Some location x. It's a vector. Now again, without loss of generality, the photon propagates in the z direction. B perpendicular to z. Right. So that means that epsilon and also A, this is where, are in the xy plane. Yeah.
What have you written here?
Now I'm looking.
I'm struggling to understand. The
Epsilon is the polarization vector.
no, the left side, just on the left side.
Assume A. Assume we have a state which is A up. Okay, A up at some location x in space. Right. We have a photon. I measure the photon. I know it has some polarization A up, and I'm assuming that the photon propagates in the z direction. And so because it propagates in the z direction, that means that the polarization vector, and because of that also A, right, because A is constant times polarization vector plus the wave, are in the xy plane. So far so good?
Yes.
Nothing should be alarmed. So as a function of time, what's going to happen to the polarization vector?
Wait, how can you measure it's A up because if
I assume it is an A up, right?
but how can you know if it's
I don't know.
okay?
I just assume it is. Okay. Now now the photon propagates. So some time passes. Which direction will be the rotation here? X changes, right? Which direction it will be? X, Y. This is the polarization. I have which direction with time? Like that. Polarization will go like that. And so with time, the polarization direction will rotate what we call counterclockwise. There'll be a counterclockwise. That is called a right-handed circular polarization.
Don't have a freedom on choosing the x direction, y direction, such it will be always counter.
It's always a right-hand.
Okay.
So I always use a right-handed coordinate system.
Yeah, but if you are choosing
And it moves in the
x.
plus z direction.
okay. So
Yeah.
If you move in the inner products here, we have don't we have minus like the 3 dimension?
No, I don't think so. I think I got it right. Cosine and sine.
המכפלה 1 מינוס 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 או מינוס 1 1 1 1.
מה?
המכפלה הסטנדרטי שכאילו
What we said, the standard one that we're using, right? It's a plus minus minus. Sorry, yeah, plus minus minus.
plus minus.
Yeah, but it doesn't matter because I'm looking only at the spatial part. The time part doesn't matter.
אבל אז אתה הולך אחורה, כאילו ככל ש-x גדל, אז כאילו זה...
לא, כי יש לי פלוס קוסינוס. מה שמשנה זה החלק היחסי, פלוס קוסינוס, פלוס סינוס, פלוס קוסינוס, מיינוס סינוס. Okay, think of that. No, I'm fine. I'm fine. This is x. No, I'm good.
No, I
So
mean,
z will be here. Z will be toward me. Right, so this
But
will be, if I'm putting the polarization in the direction, it will move like that. Right-handed, that's okay.
But I mean, but when z increases, the phi is decreases because there is a minus. It's minus pz xz. Okay.
I think there was an. Remember when I defined it with an epsilon plus and epsilon minus, there was, for the plus, there was an extra minus
Okay.
outside. That's what you're referring to.
Maybe. Okay.
Look at the notes, there was an extra minus sign. It increases. And of course, A minus, so A down is left-handed. Circular polarization. Which is exactly what the electric field is going to do. Right-handed means what? I'm putting my thumb, my right-hand thumb in the direction, in Z direction, and then the polarization will change according to the rest of my hand. That's the right-handed. And the left-handed will be exactly the opposite. Okay? So, and that goes the same as the electric field, right? E goes minus dTA, so it will change according to the left hand. So the arrows, in that sense, represent the direction of rotation relative to the direction of motion. So, direction of rotation relative to direction of motion. Yeah.
Wait, why is E the negative derivative of A? I mean,
Why not?
why yes?
Why yes, because that's the way it was defined, unless I got something completely wrong here.
Wasn't it defined as
Because you have nabla E plus dTA equals 0. Go back to the. This. Okay, now it's getting more and more interesting. Now let's look at the thing which you call helicity. So this direction of rotation relative to the direction of motion is called helicity. Let's see how it goes.
To the spin,
What?
the rotation is connected to the spin.
Yes, I'm going to show it to you. I promise you. I won't go home today before I finish.
Maybe that's what they mean by, until now there wasn't a classical, כאילו לא הייתה השוואה בין ספין לבין מונח קלאסי של תנע זוויתי.
נכון.
אז אולי זה בדיוק?
כן, זה בדיוק. Okay. You make a good point. The association of spin, I mean, you were told in quantum mechanics, guys, listen to me, huh? You were told in quantum mechanics that spin represents internal angular momentum. Right. You are not proven that. It is proven as part of quantum field theory. You were not lied. Instead of telling this is a correct statement, the full proof is only within the framework of quantum field theory. Okay? חבר'ה, שאלות אליי.
שוב, מה קרה שם? למה אי שווה מינוס?
תפתור את זה, משוואות מקסוול.
אוקיי. אוי.
אוי.
לא חשובים, לא כואב.
Okay, helicity and spin. So, how is Errol this story relates to the spin? So, we have two polarization states, right, which we denoted as epsilon up, which is 1 minus I, and epsilon down, which was 1 plus I. I'm going to argue that these two states have a well-defined angular momentum in the z direction. Claim the two states up and down have a well-defined angular momentum in the z direction. So,
angular momentum not supposed to be perpendicular to
hold on. Wait.
Okay.
I like it that you're fascinated by that. You have to wait. It will be clear.
What are you trying to do here?
What?
What are you trying to do here? To get
I want to claim, we showed that there are two polarization states. I want to connect them to the spin. So the way to do it, I'm going to claim, I'm claiming already, that these two states have a well-defined angular momentum in the plus z direction. Okay? Therefore, if they have angular momentum in the z direction, they are related to an angular momentum. But they are intrinsic to the photon. So, for that, we start by looking at the representation of the angular momentum operator in Cartesian basis, right? So, representation of angular momentum in Cartesian basis. So the basis is the simplest one, right? 1, 0. Epsilon 2 is 0, 1. This is the same basis that we use to write the epsilon up and down. Right? Simple. Now, if I want to take a system and rotate it in the z direction, right? Rotating a system in the plus z direction at angle delta phi. Right, I have that. I want to rotate it in the z direction at an angle delta phi. Right, this is the z direction. I'm rotating it around the z direction at delta phi. Right, how do I write it? How do I make this representation in this basis? Rotation, right? So the rotation matrix is going to be will be cosine delta phi minus sine delta phi, sine delta phi, and cosine delta phi. This is a representation. This is a representation of the rotation. There are more than one way to represent the same rotation. But here I can do it.
Every matrix in
Now,
SU2 is working.
Wait, what's that? Delta phi is very small, so I can approximate it. It's an infinitesimal rotation. If it's infinitesimal, then what's going to be equal to?
1 minus
1
minus delta phi.
minus delta phi, and 1. So delta phi is very small. Right? So I can write that as 1 plus I delta phi jz. This is a matrix. What?
The identity
This is the identity matrix.
Times the Pauli
And jz is an operator, right, representing the z component of the angular momentum.
It's the Pauli matrix, right?
Yeah.
One of them.
another name for that matrix, which I expect you to tell. That is also called the generator of the rotation. No. You learn group theory? יוצרים של חבורה?
Yeah, obviously.
Generator? Okay. Explain. So this is called the generator of the rotation of the group. Essentially, it is what it's what written here. That means that when you take infinitesimal rotation, infinitesimal operation of a group element, right? Then you will present it as infinitesimally small parameter multiplied by something. And that something is called the generator. It's called the יוצר החבורה, the generator of the group, and the set of all this. Let me finish because we're running out of time, and then I'll give a more thorough explanation on that. J, that is called the generator of the rotation. Okay, so how do I write JZ in this representation?
0,
JZ is will be equal to
0, 1, minus 1, 0.
0, I minus
0, I minus I and 0. Right? Because I wrote this matrix as 1 plus I delta phi JZ. 1, 1 is the identity matrix. That's what it really means. Plus I delta phi JZ, right? So there's an I here, so JZ needs to be equal to that to fulfill this equation. Now what happens when I take this operator, JZ, and I apply it to the epsilon up and down, up arrow and down arrow? What do I get?
Eigenvalue.
So JZ applied to epsilon up is equal to 0 I minus I 0, 1 minus I, which is equal to what?
1 minus
1 minus I. So it is equal to
1
epsilon up. And when I take JZ and apply it to epsilon down,
minus
1 plus I,
minus
1 plus I, so this is epsilon down, minus.
They are eigenvectors.
Right, so what did I just show you? That epsilon up and down are eigenvectors of JZ, right, with eigenvalues, eigenvalues plus 1 or minus 1. Which means what? That when I measure the angular momentum in the z direction,
either that
I get either plus or minus 1. Right? Now, what are these epsilon up and down? They represent the polarization of the photon, right? So they are not associated with its motion. I did not say anything about the motion, just that these are internal degrees of freedom. Right? So these internal degrees of freedom, right, are associated, right, with internal angular momentum in the plus and minus z direction, which is spin. Okay, so since epsilon up and down
JZ זה מטריצת פאולי בכיוון Y. לא? כאילו כפול מינוס.
שוב, זה עניין של הגדרות. כרגע אני לא מתעסק עם מטריצות פאולי. מטריצות פאולי יש להם משמעות קצת שונה מזה. So, epsilon up and epsilon down represent internal degrees of freedom. So they have eigenvectors. They are eigenvectors of Jz, which represents the angular momentum of rotation in the z direction, associated with the z direction, with rotation in the z direction. Right? We just that is what we showed here. Right? This matrix, and so they are eigenvectors of Jz, namely of the spin operator. And not the orbital angular momentum. Now we chose that the photon is moving in the z direction. This was an arbitrary choice. The photon could be moving anywhere. So we define the helicity h is the normalized spin in the direction of motion. So this is s dot p divided by p. Basically the projection of the spin in the direction of motion. Then we get h here is equal to plus minus 1. Okay, now I put a few comments. So the definition that the photon has a spin 1 is not going to change. It's not an arbitrary. You cannot say that the photon has a spin half, which confuses some of you. So that you look at the polymetry says for spin half. Here the photon has a spin 1. Right, we could multiply Jz by a constant, but it would not change anything because we could also change delta phi by the same constant. Right. Of course, the definition of directions is arbitrary. It's our choice. It just makes it handier. Yeah, and the convention is somewhat arbitrary in the sense that if you look at different textbooks, you may find that different definitions of opposite definition of right-handed and left-handed. But this, I think, today becomes the standard. Epsilon up would be the right-handed and down would be the left-handed. Okay, I think this is a reasonable place to stop, though it's way less than I was hoping. Now I will say one thing. I did put some mark here. Right, there are two things here which are relevant. One is basically, I already mentioned it to you, but I did not really prove it because we don't really have the time to prove it, is that symmetries are associated with conservation laws. Basically, it's actually the opposite. Conservation laws follow from symmetries. When there are symmetries, then when we see a symmetry, that means that something is conserved. Basically, that's a general. This is called nature theorem, and a lot of physics can be built out on that. That's the first thing. The second thing is that we have two types of symmetries. There is a continuous symmetries, like rotation, and there is discrete symmetries, such as time reversal or mirror symmetry. If we look at the mirror, there are basically, if you look backward in time, there is a symmetry, basically. Well, we wish, right? We cannot get younger, we can only get older. But generally, now, when we look at continuous symmetries, which is what I did here, right? Rotation is a continuous symmetry. We can always build a continuous symmetry from a infinite sum of infinitesimal transformations. So if we have some, so. A symmetry, a continuous symmetry, can be expressed by writing the wave function as psi goes to psi prime, which is u psi. U is some operator, right? For example, u, the operator u, could be correspond to rotation. U could correspond to a rotation.
It's supposed to be unitary.
It's unitary. Like in this case, it doesn't really have to. Here it doesn't matter. So when we have a finite continuous symmetry, like rotation in a finite angle, which is a good example, right? We can always build it up from a series of infinitesimal transformations. In other words, we can write down u of epsilon is 1 plus I epsilon g. Right? This is an infinitesimally small parameter. This is delta phi to make it infinitesimally small. And g is an operator which we call the generator of the transformation. The generator of the transformation.
Same as the JZ.
Yes. Okay, so we said that JZ is the operator that generates the transformation. In that case, is rotation around the z-axis. Okay, and we just showed, the whole point was to show that these internal degrees of freedom here correspond, have a well-defined angular momentum in the z direction. Therefore, we associate them with the internal angular momentum, namely speed. Okay, we're getting a little bit more abstract and a little bit more technical. Some parts of the course are like that, some parts are less, more descriptive. I think it's fun. If you can find it confusing, make sure that you repeat these things at home and make sure that you. Now, I was in general hoping to do much more. So I'll see what to do with problem set, because I want to give a problem set when we're finishing something. Okay, but we do have a shorter than regular semester, so we'll need to think of how to compensate for that. All right, any further questions? Yes.
What about units of angular momentum?
What about it?
Where is h bar?
It's outside, right? This operator u, it will be, I multiply it by some constant which will take all the units.
H1 is 1.
What?
You just assume that
Here h1 is 1, so you don't care. But if you, in general, when you look for units, you'll take that and you multiply all that by h bar or whatever you want. I'm just looking at the mathematical structure.
But where does the value of h
bar is 1, but we'll be multiplying here. We'll multiply this operator by some constant.
But throughout all the way that you went, there wasn't an H bar anywhere, I think.
H bar is equal to
That
1.
was everywhere.
H bar is equal to 1. So
Yeah, let's put it back. Where did we lose it, or didn't we?
Oh, that.
Where did it start from?
Where did it start from? When I turned the classical equation into a quantum mechanical equation, I turned P mu into an operator, then there should be an H bar there. But actually for photons, I won't even have them because it's all equal to 0. So I can just remove the H bar, take them to 0.
In the exponent, yours e to the I, px,
I,
and your
px,
x.
yeah, there
so
should be an H bar there somewhere.
it must be like
Yeah.
What is the definition of the S vector?
Of the what?
S vector, spin vector. Like, what is the exact? If we get
Again, I just showed you. No, this would be. These are the polarization vectors. This is polarization of photons, right? Now I said I have two options. I can either use X and Y polarization, right? Photon is staying moving in this direction. Polarization is always in that direction or in that direction. Or I can take a circular polarization, right? 1 plus I, 1 minus I, right? And then what will happen is that as the photon propagates, the polarization vector will rotate, which is what you're used to. I did not tell you anything which you don't know. What I did which you don't know, I told you, if I'm looking at these polarization vectors, and I'm looking at the angular momentum operator, the generator of the angular momentum operator in the z direction, these are eigenvalues, eigenvectors of that with eigenvalues plus minus 1. Right? Therefore, they have an interpretation of angular momentum with plus minus 1 spin, basically.
Is spin only defined for eigenvectors of epsilon? Like if we have a superposition of the epsilons, which should be allowed, like what is the meaning of that in that case?
Then it will not happen. It's not an eigenvector of this. It's not an eigen. Yes, it is not an eigenvector of the angular momentum, basically. Right? Superposition.
Okay, so S is only defined for eigenvectors.
Well, what I wanted to tell you is that this polarization have interpretation of people told you that photons and particles have spin, and somebody told you this spin really means an internal angular momentum, but they never showed you why this is so. Right? I just showed it to you. I just proved it to you. This is an internal property which obeys what you'd expect from an eigenvector of an angular momentum. Now, if you're in superposition, that's fine. You don't have to have a well-defined angular momentum in the quantum state. You can have multiple, right? I mean, you will have a well-defined, but you can be in a state of superposition states, which is fine. Okay?
Can
Yeah.
I ask a question?
Yes.
You showed us earlier symmetry of the gauge symmetry, call it a thing that you can add thing to the form to the potential, the wave equation of photon that doesn't change it.
Yeah.
And we know from Nether's theorem that each symmetry corresponds to a single fundamental force. So is it the one responsible for the electromagnetic force?
No. Nether theorem does not show that symmetry corresponds to a force. It shows that the symmetry corresponds to a conserved quantity. It's not the same thing.
I meant not a force. I meant the conservation of the electromagnetic charge. Sorry.
No, this does not. No, this does not correspond to conservation of charge.
So which symmetry does correspond to the electromagnetic charge? We learned it, or?
Ask me that on Thursday, if I don't give you an answer by that.
Okay.
Then we'll learn a little bit about discrete symmetries. But I don't think,
And
I'm not sure there will be
you
a
showed
symmetry
us-
corresponds to that really. Yeah.
and you showed us that the wave equation of the photon doesn't change if you add multiplication of the form momentum of the photon. So the other instances where I need to להתייחס to all of the possibilities, or can I always choose a single B that represents the shell?
It's your choice of gauge, right? As long as if you choose to work in a Coulomb gauge, you select a certain value of FB, and that's it. But you can select anything else. You just call it a different gauge. And
So
just
can
the
I always
calculation of the
choose a
physics will be-
single one? Aren't there any instances where I need to take care of all the possibilities of
No. Physically, it's not going to make a difference. It's just your calculation might be much, it could be much more complicated for this part. It could be easier for if you want to do a different calculation. That depends on, a wise selection of gauge really means that, for the problem you're trying to solve, will just makes your solution easier or harder. But it's not going to change the physics. It will just make it more obscure or less obscure, depending on which gauge you choose.
Okay, thank you.
Yes.
Given a photon with spin in the z direction, do we know if it has a spin in the y direction or in the x direction as well? Is it possible? And if it's not, where do we see that?
You mean the photon is propagating in the z direction?
Yeah.
I don't think it have a spin in the z direction if it's propagating in the z direction. Because the polarization vector is always transverse. You're basically saying, what if I have a photon with a polarization which is, no, you'll not be able to have it. You can have it in a massive particle, but that we'll see. I hope you have time to show that. Maybe next week. If you add up mass, then you add up an extra degree of freedom, then you can have in a direction. But I think for photon you cannot have it. Because you always have this transverse.
Do we have an uncertainty in the momentum of the photon? So,
certainly in what sense?
That we can choose the z direction to point to the photon.
No, you can't point. No.
We can't
No. We cannot measure. The photon is still there, right? The photon that comes from a star to us, millions of kilometers away, it's going in a certain direction towards us. Right? There is some probability that the photon is everywhere in space, but of course it's in that direction. Okay, guys. See you on Thursday. כן, אפשר.